When I talk about the potential for classical biocontrol of fall armyworm using one specific parasitoid, Eiphosoma laphygmae, in Southeast Asia, there are many people who participated in the study I'm going to present. I'm not going to mention them all, but there are people in Latin America where the parasitoid comes from, in Ghana where we release it, in Switzerland when we rear and study it, also in Pakistan where we made some studies, and also thanks for providing insects to some of our colleagues. So classical biocontrol is the introduction of a natural enemy of exotic origin to control a pest, usually also exotic, aiming at a permanent control of the pest. That's an important information to keep in mind. It's not all biological control. It does not include native species that you are releasing regularly, like or trichogramma or other things, or biopesticides, or conserving a native natural enemy. It's really the introduction of a natural enemy, parasitoid or predator, for permanent establishment. So there are some advantages in these techniques. Usually, well, it's an area-wide control, so you release it at one place, but it spreads by itself to the region usually. There's no need for repeated release. So at the end, even if it costs a lot at the beginning, there are huge benefits when it works because control is continuing year after year without further cost, and there is usually no cost for farmers. The costs are covered mm, by government organization, international organization, and so on. It's usually environmentally friendly when it's done correctly, not when you release a polyphagous species that may attack native species, but when it's done correctly with specific natural enemies, it is environmentally friendly, at least much more than the pesticides which it will replace. There are some constraints. Of course, this involves the introduction of exotic organisms, so there are lots of regulation constraints depending on the country. These can be strong or less strong. There is also a need for risk assessments, I say, because we want to be as safe as possible, and usually you need quarantine facilities in a place or another to study these organisms. So international collaboration is needed. You cannot do classical biocontrol on your own in your lab. You need collaboration between the region of introduction, the region of origin, and so on. And so usually when it starts from scratch, it's a long process and it's often costly. At first, I would say, the first time you try a biocontrol on a new organism, then it can be very costly because you need all the research before. Of course, when you repeat the success everywhere, then it becomes cheaper and cheaper. So yeah, there are a lot of successes in the world on classical biological control. I just want to mention one very important one for agriculture, which is the one of the cassava mealybug and its parasitoid Epidinocarsis lopezi. As you may know, the cassava mealybug was first found in Africa in the 70s. It took several years to understand where it came from and to find the parasitoid that would control it. But once it was found in South America, it was released in Africa, and within a few years, it controlled the entire problem, which really saved the situation of millions of farmers depending on cassava. So the cost-benefit ratios, it was calculated in the 70s, was already at that time between 1 to 200 and 1 to 500, despite the fact that the biocontrol itself cost a lot at the beginning. The benefits were far more than the cost. And and what is interesting is that in the 2010s years, the cassava mealybug was also found in Southeast Asia, and of course, because of the success in Africa, the parasitoid was also released in several Southeast Asian countries, and the success of the project was repeated also in Southeast Asia at much lower cost and much faster. There are many other examples of the of successes in classical biological control. We calculate until 2010 that there were more than 6,000 introduction of insects agent against almost 700 insect pests. It must be much more now. And there were about 27% of the insects controlled. This may look a bit low, but this also includes projects that were badly managed or stopped before the end and things like this. So in general, the success may be higher, although you never know in advance if it works. So we have to be realistic. Sometimes we also invest quite a lot of money for projects that at the end don't work, but that's the risk. Classical biological control of fall armyworm is not. I don't know if you see this green and red stuff in your screen, but in mine it's just in the middle. It's a bit annoying.
That's okay. No,
It's
we
okay.
don't see that.
Oh, you don't see it.
No,
Okay.
no, it's perfect.
Sorry, because I have this kind of thing in the middle of my screen. Okay. So yes, classical biological control of fall armyworm is certainly not easy. It's and certainly not a silver bullet as it has been for many other pests, including the cassava mealybug. First, because fall armyworm is a pest in its area of origin. We have to be realistic. It's also a pest in Latin America. In America, several publications report low incidence of natural enemies, although this I think that this is a bit misleading because the surveys have done a little bit that have been done are usually biased towards non-parasitized larvae. And also in Africa and Asia, fall armyworm is already attacked by a complex of parasitoids and other natural enemies. And some people may ask, yes, but if we have already parasitoids and predators, why do we have to introduce new species? We still think it was worth. We still thought it was worth trying. First, because classical biocontrol is at no cost for farmer. That's a very important thing. If it works, it just farmers can just profit of it. Even a general decrease of population levels by 10-20% would have huge benefits because of the huge impact of fall armyworm and the widespread impact of fall armyworm. If you decrease the population of fall armyworm by 10-20%, you may go below the threshold of incidence simply because also the total control of fall armyworm is not necessary. Now we know very well that minor damage on maize usually does not result in yield losses. So if you increase the mortality by 10 or 20% by introducing a new parasitoid, that may have huge effects on the large range. And we also have to say that population levels are lower in the Americas than in Africa and probably in Southeast Asia. And the role of natural enemies is usually underestimated. As I said, when the studies are done on natural enemies, in most cases, they collect very obvious large larvae, which are not the ones which are parasitized. And they usually neglect small larvae which are hidden in the walls and which are themselves then parasitized. And finally, fall armyworm is a huge pest with serious impact on livelihood, including human health. So we have to try. This is one tool that we cannot neglect. Starting with that, oh yes, I just want another point. There are some other cases in the history of classical biocontrol where we found that some invasive pests became less damaging in the area of introduction than in the area of origin after classical biological control. So we cannot exclude this as well. So which natural enemy to choose in the Americas to conduct a classical biocontrol? There are lots of parasitoids, predators, and pathogens. We immediately excluded predators simply because with fall armyworm, all the predators which occur in Latin America are not specific at all. In some cases, predators can be. For example, there are some predators of scale insects which are very specific, but in this case, there was none. So we focused right from the beginning on parasitoids. There are more than 50 species of parasitoids on fall armyworm in the Americas, and which one to choose? Well, the main criteria for selecting classical biocontrol agents are their efficiency in all environments. They should be the most frequent or very frequent and very abundant in the area of origin. And the specificity, which is a very important criterion because we don't want non-target effect on native species in the area of introduction. And then other factors that need to be checked is climatic suitability. Right? It needs to be climatically suitable. The the region of introduction must be climatically suitable, and it's also better to fill in empty niches in the area of introduction. For example, if you have a lot of parasitism by egg parasitoids, you may want to introduce a larval parasitoids and so on. And so we looked at the parasitoids that were the most frequently cited in the literature, and these are the ones. And we first looked at the literature for the two main criteria, the abundance frequency and the specificity. For the abundance frequency, clearly the one which was the most abundant and frequent in many studies was Chelonus insularis, which is an egg larval parasitoid. But depending on the region, you also had several other species which are mentioned here, which are also frequently abundant, sometimes more than Chelonus insularis. And regarding specificity, according from the literature, the one that appeared most specific was Eiphosoma laphygmae, an ichneumoniid larval parasitoid that looked very specific from the literature, and also Chelonus insularis and Aleiodes laphygmae, which show some specificity with a shorter list of potential hosts, while the others appeared, at least from the literature, not specific at all. We also looked into different countries, particularly Bolivia and Nicaragua. We did our own surveys, and in Bolivia especially we worked, and we found out that in Bolivia the most abundant parasitoids were Chelonus insularis, but also Eiphosoma laphygmae, which was often more abundant than Chelonus, and the big larvae were also attacked by two tachinids. In Nicaragua, it was clearly Chelonus insularis that dominated. So we started to work on Chelonus insularis because it is the most frequent, Eiphosoma laphygmae because it is the most specific. We also included Campoletis species because it is the one that is usually most abundant in cool areas, like in high altitude or in low and high latitude, in subtropical areas. We quickly found out that Chelonus insularis and Campoletis species in the lab were not specific. They would attack quite a lot of other noctuids. So since at CABI we are very we have quite fussy about specificity and the risk of non-target effects, we focused almost exclusively on Eiphosoma laphygmae. But we still keep an eye on the Campoletis species for European purpose and for high altitude purpose in Africa. So Eiphosoma laphygmae, this is indeed one of the most abundant parasitoids in the Americas, but there are important regional variations. If you go to Brazil, Bolivia, Peru, it is often the most abundant parasitoid, sometimes the most abundant, with average parasitism in the literature of 10-20%, but again, with the limits I mentioned about the methods of sampling, because in our samplings in Bolivia, we clearly had a percentage higher than that, 30-40% parasitism. It's also frequent in Central America, so climatically it's okay, but it's usually less abundant than the numbers we have in South America. It's absent in the USA, northern Mexico, and Argentina, maybe because there the fall armyworm is mainly transient, and since it is a specific parasitoid, it cannot adapt in regions where fall armyworm is transient, or maybe it's just a question of climate. We don't know exactly. There is also no congeneric species on fall armyworm in Africa and Asia, which is of course an important factor as well, because like for example, Chelonus insularis, there are Chelonus species which are the most abundant parasitoids in Africa and Asia as well. But in this case, there is no Eiphosoma in Asia and Africa, which is another good important criterion. It's probably the most specific parasitoid of fall armyworm. in Bolivia, where we did most of our work, in field work, we collected other 10 noctuids in the surrounding of fall armyworm infestation, which were full of Eiphosoma, and we didn't find Eiphosoma on other noctuids, including some other Spodoptera species, such as Spodoptera iridania. So in the field as well, its ecological host range is probably restricted to fall armyworm. In the literature, as I said, it's totally specific. We have two records on hosts mentioned only once, but not well described studies, just mentions on two Lepidoptera, which are quite well known and which have been studied for their natural enemy several times, and only once they mentioned Eiphosoma laphygmae, which may be a mistake. But we wanted to test by ourselves. So we established a rearing in quarantine facilities at CABI in Switzerland with specimens from Bolivia, and we made specificity tests. We started with the most complicated options of the specificity test, which are the sequential no-choice tests, which means that we offer females naive, which means they have never encountered the host. We offer fall armyworm during 4 days, and then during 2 days we offer them the non-target species, and then again during um, 4 days the fall armyworm, and only females that successfully parasitized fall armyworm before and after the non-target were taken into consideration. We could, with these things, this requires a permanent rearing of other hosts. So we tested this only on 3 different Spodoptera species: Spodoptera litoralis, which is mainly an African species; Spodoptera latifacea, a South American species; and Spodoptera exigua, which is present in several continents. We had 0 successful attack on litoralis and latifacea, and we had 4 cocoons obtained from Spodoptera exigua, among many others. No adult emerged. But we wanted to test much more, especially non-Spodoptera species as well, because Spodoptera are also pests usually. So we also want to know what they are doing with non-pests. And then we opted for an easier method, which is the parallel launches, which is much easier test. So we just offered to females, we just offered different species. Different females were offered different species, and we tested 16 species, and we tested for the oviposition rate, which is the percentage of females ovipositing in larvae within 15 minutes, and rate of parasitism. And no, sorry, rate of successful parasitism. And so here are the results. You can see that the non-Spodoptera, they were sometimes attacked. So the blue bar is the percentage female ovipositing. So they were attacked sometimes. They tried, but less than for the Spodoptera species, which are on the left, and there was no development at all. While on the Spodoptera, we had 3 successful development in Spodoptera litura, and 1 emergence, but not but only 1 emergence, and it was so the development was much less in comparison to Spodoptera fujiperda. We also did some tests in our CABI facilities in Pakistan, where they reared Eiphosoma for at least a year. They made some bulk rearing in bigger jars, and they offered 45 larvae to different species, including two non-noctuids. They got over 50% parasitism in Spodoptera fujiperda, none in the non-target species. So in summary, we can say that our study suggests that Eiphosoma laphygmae is highly specific to Spodoptera fujiperda. In vials, it can attack other species, especially other Spodoptera species, but successful development is not observed except in very rare case in Spodoptera exigua and Spodoptera litura, but this was of course in a very confined environment in small tubes. So we are really confident that releasing this parasitoid would not lead to non-target effects on native insects. So then we decided to apply for field releases in Africa. We started in this case in Ghana. We got the release permit based on our studies. There, there is no quarantine in Ghana, so we cannot rear them for further tests. They tried some rearing in the lab, but so far it failed. It also failed in Kenya and Zambia actually. And so for the moment, what we are doing is we are trying to produce cocoons and shipping them little by little to to from Switzerland. We started only some months ago, and so far we have released about 200 mated female. It doesn't look a lot, but you can have successes in classical biocontrol. Sometimes in the records we have successes with 8 females releases in other projects. So this so a few hundred could be plenty enough for establishment. It's still not so easy, of course, with this system. We are starting also the post-release sampling. So far, we haven't found them back in the field, but this is not uncommon at all. In most cases, in classical biocontrol, you only get records of establishment after 1 or 2 years, sometimes even longer. So that's not unusual at all. Um, what is our future work in Africa? We want to release much more female in Ghana in 26 and check establishment. We also want to improve the production and handling methods because again, we sent 365 cocoons, only 200 females were released because also with the shipment, and so there was 50% mortality, 30% mortality in the first 3 days as adults, and so on. So, and the sex ratio is not totally 50%. So yeah, we need some improvement here and there. We are going to retry the rearing in Kenya because, of course, it's much more efficient if you have the rearing in the country and can release once you have a lot of insects. Because sometimes we have a lot of cocoons, but in Switzerland, but we are not prepared for shipment to Africa. So it's much better to have to retry the rearing in Kenya, possibility also in Ghana and in Zambia. In Zambia, there is a slow regulatory process because they don't have regulations for classical biocontrol, and so we help the country in getting these regulations ready. But the plan is to rear them and to release them in Ghana, Kenya, and Zambia. And so we were discussing in Southeast Asia, a couple of months ago when I was in Malaysia, and we said, why not trying in Southeast Asia? Eiphosoma is a tropical species, and the climate in most of Southeast Asia is likely very suitable. Eiphosoma does not like maybe in some African countries it may have difficulties because it I don't think it's also because it's very specific. I don't think it likes very long periods of drought, for example, without any rain when there is no fall armyworm at all in the area. Some people have tried to do the climate species development models including with Eiphosoma, but we don't know so much the climatic needs for Eiphosoma laphygmae. We can just extract them from the distribution. So these models, this one and some others, also made by some other colleagues, have to be taken in with caution. But you can see here in red that most of Southeast Asia, especially Malaysia, Indonesia, the Philippines, and Vietnam, Laos, south of Thailand, seems highly suitable. I think these maps are also quite conservative because they are based only on the distribution in the area of origin. So this is, but I really think that because it's a tropical species, because the drought are much less severe in Southeast Asia than they are in many African countries. I think Southeast Asia may be even more suitable than many African countries. Also, what a very important argument is that, of course, classical biocontrol is costly when you start from scratch, but most research has already been conducted. Like, the surveys, the rearing, the biology, specificity, efficiency, all these studies have already been done. So implementing in Southeast Asia would not be very costly anymore. And the benefits, as I explained earlier, can potentially be huge because of the very wide spread of fall armyworm. So how to proceed? Well, the most important hurdle and discussion is, of course, the regulatory issues, because importing an exotic agent is never benign. So, and I have to say that the regulation related to classical biocontrol can be very different from country to country. I'm not very familiar with regulations in Southeast Asia, but everywhere in the world, it really depends on the country. Some countries are very flexible and have regulations. Some countries have regulations which are very strict. Some countries don't have any regulation on classical biocontrol, which may mean that they don't care, that they don't mind releasing. Some just don't want any exotic organism. So this has to be fixed. And also, we have to see if quarantine facilities exist in the country and if they can be used for biological control agents, because facilities may exist for pathogens and so on, but not for for biological control agents. So if quarantine facilities exist, will the country require additional tests? So in addition to what those we have done in Switzerland and Pakistan before approving the release or not? And if there is no quarantine facility, we have to consider that importation is like release. If you import and rear in your own lab, which is not in quarantine, it means that the parasitoids can escape. So so importation and release are more or less equal. So in this case, biocontrol agent will have to be imported clearly from a quarantine facility abroad in Switzerland or in Southeast Asia. Then, of course, the next step would be to set up the production unit but is it in several countries or in one, distributing the parasitoid to others? That can be also discussed. It should be in quarantine if possible, because this has implications for permits, as I said. Then, of course, we can ship it to Switzerland. There is also, I mean, the agreement with Bolivia, because Bolivia allowed us to release it elsewhere. They are very friendly, and then we may have to collect some more to refresh the rearing, which now the last collections was done 2 years ago, so we may want to refresh with fresh specimens. And then, of course, we are available for for training in production technique, either in Southeast Asia or even in Switzerland. Then, of course, you have to release them, but before release, it's important to know the parasitoid complex of fall armyworm in the area that where you are going to release, because this needs to be known before the release, so that after the release, for the post-release assessment, you know what was already there before. And you have to find release area where fall armyworm is present the whole year to facilitate establishment. After, of course, they can spread to other regions, but at the very beginning, to facilitate establishment, it's easier to have to release them in places where the climate or irrigation allows fall armyworm to be abundant during the whole year. And then you have to do, very important, the post-release assessment on the establishment, but also on the impact. So this is my last slide. Take-home messages. Eiphosoma laphygmae is the most specific parasitoid of fall armyworm, unless we discover something else in Latin America that thought to be one species and are several specific species. I don't know, but so far it is. In its native range, it is among the most abundant parasitoid of fall armyworm. It has been approved for release in Ghana and very soon in Kenya and Zambia. In Kenya, it's already more or less done. We have the verbal agreement already. In Zambia, we still need to to help with procedures. Most areas in Southeast Asia are likely to be climatically suitable for its establishment. Most studies have already been conducted, surveys in the native range, biology, specificity, rearing methods, etc. So a classical biocontrol could be conducted in Southeast Asia with limited funding, in contrast to if you had to start with scratch. I have to say, I mean, I have to be very honest, Eiphosoma laphygmae is not a silver bullet for fall armyworm, but it may help reduce fall armyworm population regionally over very large scale, which of course then leads to huge benefits. The selection of countries and areas to initiate a biocontrol program may depend on the legislation in place, the availability of a quarantine facility, and the availability and motivation of biocontrol specialists. They are in biocontrol specialists in every country, but they need to be available for helping in this. And climate suitability, of course. Some regions are clearly more favorable than others. So with this, I'm finished. I'm ready for to answer questions. I just would like to say that this study has been done in the framework of our Plantwise Plus program, and and uh, and since a few months, I'm also working on this topic in the framework of an EU-funded project, EU4 Ready, more specifically for Europe. And therefore, I'm also trying to look at other parasitoids which are more subtropical species than Eiphosoma. So thank you very much. I
Excellent.
put
Thank
back,
you, Mark. Yeah,
yeah,
put the take-home messages. I was just going to say, leave them there.
yes,
So perfect. You have lots of questions, and I'm sure there's going to be more coming in. And that was wonderful. You've got 165 participants in the room. So there we go. That's fantastic to see everyone. Let's start with some of the questions. They're in the Q&A box. And I have a question too, because you said that the levels of fall armyworm parasitism observed under field conditions in the countries of origin was perhaps underestimated. Why do you think that is? You said there was sort of maybe a bias. Is it because of just capability, or is it because people would rather use another solution, or what's the sort of reasons for that, do you think?
well, it's often, not all the time, but I found out that it's over and that it's often yes, underestimated because usually when you calculate parasitism, I mean you collect the parasitoids you find in the field, and if you collect parasitoids in the field, you mainly find the big larvae or the larvae which are most active, and these are not the ones which are parasitized. So the ones which are parasitized, they are not active, they are hiding, they are smaller, and most parasitoids, especially the hymenopterans ones, they kill the parasitoid before they reach the last instars. So if you collect mostly last instars or even small instars which are most active, you don't get the parasitoids. We collected in Bolivia parasitoids, and we found parasitism rate which was much higher than any other study almost in Latin America. So I suspect that it is likely underestimated. Not all the studies, but at least some studies are underestimating parasitism, except for the big larvae which are parasitized by tachinids flies.
Ah, excellent. And so here's a question that sort of relates to that. So does it target older larval instars over younger instars? And
Oh
if
yes,
yes, does it have any influence on parasitism rates and adult emergence?
yes. The I mean, so Eiphosoma laphygmae attacks first and second instars, and it kills them in the 15th star. The parasitoids, the larvae which are parasitized by Eiphosoma are much less, feed much less than the others. They remain smaller, but they go to the 15th star and then they are killed. Of course, the damage in classical biocontrol, it does not matter. You could also use parasitoids that attack mature instars. It does not matter because in classical biocontrol, what is important is to have less less pests in the next generations. So it's not for immediate action, it's for lowering populations in the longer term, of course. But
Excellent.
this one attacks small stars and kills the 15 star. There are 16 star in fall armyworm, so they attack very small larvae and kill middle-sized larvae.
Fantastic, thank you. That's excellent. Here's a question here from Ravinda Joshi. Despite its introduction to the USA as a classical biological control agent, it failed to establish itself. So, in your opinion, what future research should be done in Asia, especially on the impact of environmental factors on parasitism success in field settings to optimize its application?
Yes, this was done in the 80s. Eiphosoma laphygmae was released in the US. I have no idea why it failed. And the people who did that, I don't know. I'm not sure if they are still available to answer. There is no information on how many were released and where they released. I think that the problem that in the US is that in most cases the climate is probably also not that suitable, except if they have released also in Florida, I would say. So I don't know. It's difficult to say, but of course there are lots of examples of biocontrol agents that have been released at some place and failed, and have been released at other place and succeeded. But I don't have the detailed data on why it failed. Maybe they released very few, maybe not really at the right moment, or just not at the right in the right climate. I don't know. But it
Okay.
was not a huge effort, I think.
Yes. Okay. Great. Thank you. Here's a question from Andy. Mark, do you have the baseline mortality data on the natural control by natural enemies before releasing the parasitoid?
Well, you need that. You need to know the mortality factors, especially the natural enemies in your release area. That is always important because you need to have a baseline data for, especially if you release a parasitoid, for parasitism in the area of release. That's important. Yes, to show that you are increasing natural enemies and to see whether there is any interaction, competitive interaction with the native uh, the native parasitoids which are already in place. So that's something that is always good to do.
Excellent. We've got some quite long questions. Yes, I just have to have a bit of a read of them. Here's a question here, a little bit shorter, and I'll come back to some of the longer questions. But here's a question here. What should be the climate conditions before releasing this parasitoid in the field?
Well, the climate condition will influence the fall armyworm availability. Climate conditions, of course, you will never release during a storm or a typhoon. But yeah, I mean the most important is to have a lot of small larvae in the field. So of course the season has to focus on the season where you have the most larvae, the most young larvae in the field.
Okay, excellent. Here's another one. Has any hyperparasitism been recorded?
Not on this one. For the moment, we haven't. In Bolivia, where we studied Eiphosoma, we didn't record hyperparasitoids on this, but on other species, yes, but so far not on this. But it does not mean that it does not occur. I mean, there are hyperparasitoids that are known to occur in fall armyworm uh, i- on different hosts. So, but not here.
Excellent. We've got a lot of questions here, Mark. So I know you're sort of in the hot seat at the moment, getting bombarded with questions. So you're doing a great job. And there's a question here which is really around, I guess, the sustainability of such a program. So can this parasitoid be developed into a scalable and operational biocontrol within IPM programs in terms of mass rearing, field release strategies, regulatory acceptance, and compatibility? I mean, you've showed us an example of how that's been done, but how easy is it to continue that sort of process? So once you've introduced it, what's the sort of cost and resources that are needed to sustain this type of approach?
Well, the beauty of classical biocontrol is that you don't need to to make permanent releases, constant release. Once it is established, you just have to pray for its effect, and it will spread by itself. I mean, this parasitoid is far too complicated to mass produce and release regularly. It's a difficult parasitoid to rear, very difficult, in contrast to other parasitoids that can be produced by millions and released in augmentative biocontrol. This one cannot. So we just have to expect that this parasitoid becomes established. Of course, you may want to release, depending uh, on its spread, it may be slow to spread. So you may want to help its spread. But once it is established in a region, uh, of course, yeah, ideally, we should stop all pesticide applications or use biopesticides or much less toxic pesticides, and et cetera, et cetera. But we should not continue forever this production and release it. I mean, in classical biocontrol, the hope is that the parasitoid will spread by itself and continue to occur year after year without any other action others than trying to limit pesticide.
Excellent. Great answer. Here's a question here, and it comes up quite a bit, and it's around concerns around whether there's any um, risk or cases that are documented where biocontrol agents that have been introduced through classical biocontrol have become pests. So how would we prevent this? And you've given some pretty good sort of take through of the steps that you take, but is there cases, what is the risk, do you think, of this turning into something, I guess?
Well, there are very few cases where it has become a pest by itself. I'm thinking of a ladybird, Harmonia xeridis, lady beetle that became pest itself on grapes in North America and Europe, but this is because it was highly polyphagous. There are some cases where parasitoid cannot become pests themselves, but they can, of course, in some cases they can attack other non-target species. They can attack native hosts, which are usually closely related to the target host, and this is why we are careful in selecting usually the most specific ones. But the worst it can do for a parasitoid is to attack other hosts. Of course, if it's highly polyphagous, it can attack some really non-wanted non-target. It can have some non-wanted non-target effects. But in this case, the the parasitoid is highly specific. I cannot guarantee that it may not attack from time to time some individuals of other Spodoptera species, but most likely at a very low level if it does. Of course,
Right,
of
excellent.
course, you always in classical biocontrol you always have to balance the risk and the benefits because if it establishes, there will be definitely benefits towards less use of pesticide, which of course will have much more impact on native biodiversity than the parasitoid, which may occasionally kill another Spodoptera
Okay,
individual.
excellent. Now we're almost out of time. I've only got 4 minutes. I've got one more question for you. And that's around, given the shared pests and the sort of porous borders that we have in Southeast Asia, uh, how important do you think regional coordination in Southeast Asia is when considering a classical biological control introduction?
I think it should, if I remember well, the classical biocontrol of the cassava mealybug in Southeast Asia was also a coordination, regional coordination. Of course, it helps. There are some countries that may not have quarantine or may not have the facilities for rearing the parasitoids. So it may be also done by the neighboring countries and release and produced and released in the neighboring country, then which does not have the facility. So that's really a possibility. Of course, if you release the parasitoid in a country by itself, it should cross the border, which of course also implies the fact that it's always better to work on classical biocontrol regionally, also for regulation issues. Because in some cases, there have been cases in the past where some countries were not happy with their neighbors having released parasitoids which they considered as risky and so on. So this may happen. So a regional coordination is always better, of course.
Excellent. Well, thank you, Mark. That sort of brings us to a really good closing, and that it sort of sums up what the ASEAN action plan on IPM, fall armyworm, is all about, is looking at regional collaboration and coordination. So it's a nice way to end, and this is something that I think is something that's really interesting to take forward and discuss as a region, as you say. So we have really appreciated you joining us today and giving us that sort of starting point of thinking about this as a potential option. And it's a very rich presentation, lots of great examples, drawing on all your expertise. And you have a lot of questions still in the Q&A. And what we might do, everyone, if we have time, it's getting quite busy just before the end of the year, we may try and pick a few of those and answer them and put them as part of the package of materials. But I wanted to thank you, Mark, and next steps will be taking this back to the task force and presenting it as an option for consideration. And of course, if anyone wants to follow up individually with Mark, you're most welcome. His contact details were there. You can also contact me and I can pass on his details, and we'll be following that up in the new year. But thank you so much. Extremely interesting. It's been a fantastic way to sort of draw a close to our webinars of the year of 2025. And actually, Mark was, I think, on our very first webinar in 2021, I think, that we had. So it's actually quite nice to sort of, for the 5 years, I think you've joined us from the start to the finish. So it's really nice to end with you this year. So thanks, Mark. And I see somebody might have put up their hand, I'm not sure, but I would just like to say with 1 minute, we're going to finish on time. It's fantastic. Thank you to all of you who have joined us for the webinars across the year and all the material and resources and things that we've put out. We really appreciate your help and input. We appreciate the support of the Department of Foreign Affairs and Trade of Australia for funding the program, and also working closely with CABI. It's always it's a privilege to work with a fantastic organisation and great experts. So thanks to FAW as well and the Southeast Asia CABI team. Thanks, Mark.
Thank you very much, and thanks to the audience. It was really nice. And as I said, please feel free to send me questions. I don't take much holiday at the end of this year, so you can send me
Don't
any
say
question.
that. You'll be inundated now. No,
Okay.
thanks. Thank you, everyone. Have a really nice end of 2025. We'll see you in 2026, and I'm sure Mark will be back as well, and we'll continue the
Yeah.
conversation. So thank you. Bye.
Okay. Bye bye. Thank you.
Bye.